Over the past 50 years, humanity has tirelessly explored our cosmic neighborhood, searching for the ingredients essential to life. We've dispatched robotic rovers to Mars to drill into its rocky surface, skimmed the atmosphere of Venus in pursuit of water, and even retrieved samples from asteroids. Despite these remarkable achievements, the building blocks of life have remained elusive. Now our attention turns to a new frontier, Jupiter's icy moon Europa, where the Europa Clipper mission, launched aboard a Falcon Heavy rocket, aims to uncover clues about the origins of life. At first glance, Europa seems an unlikely candidate for habitability. Orbiting Jupiter, far beyond our solar system's habitable zone, it's a moon slightly smaller than our own, bathed in intense radiation due to its position within Jupiter's powerful magnetic field. This radiation would fry a satellite's electronics in less than a day and makes life on the surface, as we understand it, impossible. So why is NASA investing $5 billion to send a probe to this hostile environment? The answer lies beneath Europa's icy surface, where scientists suspect a vast ocean may hold the key to life's potential. The idea that Europa could harbor life stems from evidence suggesting a massive subsurface ocean. The first hints came from the Voyager probes which, passing 250,000 kilometers away, captured images of Europa's smooth, crater-scarred surface marked by long ridges formed by moving ice. These images sparked curiosity, leading to further missions like Galileo, which provided more detailed photos and data. However, Galileo faced challenges, losing valuable data during close approaches to Io, another of Jupiter's moons, due to high-energy electrons penetrating the spacecraft and causing it to enter safe mode. These electrons, part of Jupiter's intense radiation belts, exposed Galileo to 3 times the radiation it was designed to withstand. This harsh radiation environment makes Europa's icy shell crucial, shielding the ocean below from ionizing radiation that would otherwise render life impossible. Surprisingly, this same radiation may enhance Europa's potential for habitability. The plasma and charged ions bombarding the surface create strong oxidants such as hydrogen peroxide. If these oxidants reach the ocean below, they could react with other molecules, forming a complex mix that life might utilize. Additionally, Europa's eccentric orbit around Jupiter generates tidal forces that flex and contract the moon, producing friction that could heat the subsurface ocean, potentially creating a warm environment suitable for life. The existence of this ocean was inferred from Europa's unusual magnetic field, detected by Galileo's magnetometer. This instrument, consisting of a base coil wrapped around a metallic ring core clockwise on one half, counterclockwise on the other, with a measuring coil on top, detected a magnetic field deviation that could only be explained by a subsurface ocean rich in dissolved ions. Jupiter's magnetic field, 20,000 times stronger than Earth's, interacts with this salty ocean, inducing a magnetic field in Europa itself. In 1997 and 2000, Galileo's magnetometer recorded unexpected spikes in the magnetic field during close approaches to Europa, anomalies that puzzled scientists. It wasn't until 2014 when Hubble captured a 200-kilometer-tall eruption of ionized, salty water from Europa's surface that researchers realized Galileo had likely flown through similar plumes. These discoveries fuel excitement for the Europa Clipper mission, which aims to answer lingering questions about Europa's ice thickness, tidal heating, and subsurface ocean. Originally planned for a direct 3-year journey to Jupiter aboard NASA's Space Launch System, SLS, the mission switched to a Falcon Heavy to save $1.5 billion in launch costs. However, the Falcon Heavy's lower thrust requires a longer route, with gravity assists from Mars and Earth extending the journey. Upon arrival, Clipper faces the challenge of navigating Jupiter's radiation belts. Orbiting Europa directly would reduce the probe's lifespan from 3 years to just over a month due to radiation exposure. Instead, Clipper will follow a highly elliptical orbit around Jupiter, diving into the radiation zone every 14 days for a brief, high-speed flyby of Europa at 4 kilometers per second. During these encounters, it will collect vast amounts of data before retreating to a safer region for 10 days. To transmit data back to Earth and perform orbit corrections. to withstand these radiation bursts. Clipper's electronics are housed in a 1 centimeter thick aluminum vault, carefully designed to balance radiation protection with weight constraints. Engineers meticulously arrange the instruments within this vault, playing a delicate game of spatial optimization to fit everything inside. Clipper is equipped with 3 magnetometers to study Europa's magnetic field and gather more data on the subsurface ocean. To avoid interference from the spacecraft's metallic structure, these sensors are mounted on an 8.5-meter-long carbon fiber boom, which deploys using its natural flexibility without actuators. Positioned along the boom, the magnetometers will provide precise measurements of the magnetic field in all 3 directions, offering deeper insights into the ocean's composition and dynamics. Scientists also hope Clipper will fly through another of Europa's water plumes to sample material directly from the ocean. A 25-centimeter-wide collector, open during close flybys, will capture dust particles that pass through conducting meshes, altering their capacitance to measure particle speed and origin. As Clipper slams into these particles at high speed, they break into base elements and ions, which are deflected by an electric field into a detector. By analyzing the time-of-flight differences, scientists can identify the particles' building blocks, potentially revealing organic compounds. Beyond plumes, Clipper will sample Europa's tenuous atmosphere during low passes, using a tube to collect gases ionized by a stream of electrons. These ions, propelled through an electric field, are separated by mass, with heavier ions moving slower than lighter ones, allowing scientists to identify compounds critical for life. If plumes are not encountered, Clipper will analyze Europa's surface composition using infrared and ultraviolet spectrometers, providing clues about the moon's chemical makeup. Additionally, Clipper will measure Europa's gravitational field to understand how the moon flexes and stretches during its orbit. Unlike Earth's gravity maps, created using 2 satellites to measure distance changes, Clipper will rely on a single probe, measuring velocity shifts with an 8 GHz signal sent from Earth. This method, accurate to 0.1 millimeters per second, requires a direct line of sight, which is challenging given Jupiter's size and Europa's orbit. The mission team estimates at least 10 flybys are needed to achieve precise gravitational measurements. Clipper's imaging system, featuring 2 8-megapixel sensors with wide and narrow-angle lenses, will capture 90% of Europa's surface at a resolution of 100 meters per pixel, 6 times more surface area and 5 times better resolution than Galileo's best images. These images will reveal the dynamic behavior of Europa's ice, such as shifts, pileups, or displacements, helping pinpoint regions where life might exist. A radar sounding system will measure the ice's thickness and elevation changes using 2 frequencies, a 9 MHz wave, effective for penetrating ice but limited by Jupiter's radio interference, and a 60 MHz wave, less affected by interference but more susceptible to ice roughness. NASA's experience with similar radar systems on Earth, monitoring ice sheets, ensures confidence in this technology. To power its instruments, Clipper relies on 30-meter solar panels, a choice driven by necessity. Unlike earlier Jupiter probes that used plutonium-238, a byproduct of nuclear warhead production with an 88-year half-life ideal for space missions, Clipper uses solar power due to dwindling plutonium stockpiles. Since the U.S. halted nuclear warhead production in 1988, NASA has relied on limited reserves and Russian supplies, which ran low by the time Juno, another solar-powered Jupiter probe, was built. Clipper's large solar panels, paired with batteries to endure Jupiter's eclipses, follow the successful model of Juno and the European Space Agency's Rosetta probe. Meanwhile, NASA is ramping up plutonium-238 production at Oak Ridge National Laboratory, aiming for 1.5 kilograms per year, though it will take a decade to meet the needs of missions like the Perseverance rover. The Europa Clipper mission represents a bold step in our quest to understand life's potential beyond Earth. By studying Europa's ocean, ice, atmosphere, and magnetic field, Clipper could redefine how we search for life in the cosmos. Its innovative design, from the radiation shielding vault to the deployable carbon fiber boom, showcases engineering ingenuity in overcoming Europa's harsh environment. As it embarks on its journey, capturing detailed images and data over multiple flybys, Clipper promises to unravel the mysteries of this enigmatic moon, bringing us closer to answering the profound question of whether we are alone in the universe.